These bandanas make it hurt.
The learning objective for this lesson is to determine the relationship between force, mass, and acceleration through graphical analysis based on the data that we gathered last lesson. Before we do that, we need to have a quick chat about graphs. So graphs, we draw them in science to show the relationship or the trend between two variables. Variables that change with proportional rates produce a straight line with a constant positive slope. We call this a directly proportional relationship. As x increases, y increases. We draw this, or write this out, should I say, as y is proportional to x, with that little symbol there being the proportional symbol. Another type of relationship that comes up a lot is an inverse relationship. That is indicated by a curving slope. As x increases, y decreases. However, this rate is not direct as that curved slope sort of indicates. As x doubles, y halves. We write this as 1 over y is proportional to x. Now, direct linear relationships are much better to analyse because a constant of proportionality can be easily derived. The constant proportionality is the constant between two proportional variables that determines the ratio of their proportionality. So in other words, as one variable increases, by how much does the other variable increase? Well, this is determined by the constant. Fortunately, it's really easy to figure out. It's the gradient of the line. So this then allows us to determine the value of one variable based on the other. Let's now look at a couple of examples just to get our head around this idea. So in this very simple example, we can quite easily see that our constant, which we use as k, is the gradient as the rise over run, 1, so constant is equal to 1. So we can now write this as y is equal to 1 times x. So in other words, when y is 4, x will also be 4. Nice and easy. If we were to change that gradient, we can still say that y is proportional to x, but by how much? So if we see that as x goes out 2, y goes out 1, we've got a rise of 1 over 2, which is a half. So if we did this in Excel, it would come back with a gradient equal to 0.5. It's much easier for us to use fractions when we're working in formulas here. So we're going to put this as 1 over 2. And you might need to, if the Excel gives you a value, you might need to put that into your calculator, which I'll show you in a minute. So I'm now going to write that as y equals half x with that constant proportionality there. And I don't end up liking it as a fraction. So if I wanted to, I can change this to 2y equals x. So to demonstrate this whole process, I'm going to throw in another scenario that analyzes different variables. So what I'm going to say is, what is the relationship between speed and time over a set distance? Now, if we remember from a couple of weeks back, we should actually know what this relationship is, but I'm going to show you the process to demonstrate how I do this. So here I have a table already set up with all my data values already gathered. I've got a set distance of 80 meters. I've got a changing speed going up by 5 meter per second increments, and the time it took me to cover that set distance of 80. When I plotted it, I came out with this graph that doesn't actually have a direct relationship. It's kind of, you've got this sloping, awkward slope. So I'm pretty suspicious here that I've got an inverse relationship. To confirm this, what I would do is I'm going to make a new column here. I'm going to call this 1 over time. So the inverse of the time. I'm now going to make this column equal to 1 divided by that value, d5. Now, as I drag that formula down, it's going to populate that there for me. Now, I have the speed and the inverse of time. So I should be able to graph these now. Circle the x and the y and insert my scatter graph. And wow, what do you know? That looks like a pretty good direct relationship to me. And I'm going to now add a trend line and get that value for the gradient. And my value for the gradient is 0.0125. Now, that actually doesn't tell me a great deal. Well, it does, it actually tells me a lot, but I can't, my brain doesn't work mathematically like that. So what I'm going to do is I'm actually going to put that value into my calculator, 0.0125 equals 0.0125, funnily enough. I'm now going to press the fraction button, which can turn a decimal into a fraction. It says 1/80, so that's much more useful to me. So based on that first graph, we can see that we assumed that the inverse of time was proportional to speed. And by graphing the inverse of time on speed, we could confirm that. And we were able to get a value of 1/80 for the gradient, and we could substitute that into make this equation to show this relationship. It's still a little bit awkward, and I'm going to times both sides by 80 to give me 80 on t equals s. Now, 80 is my constant of proportionality here, and I had a constant, one of my constant variables in this experiment was the distance, and the distance was 80. So clearly here, my graph is telling me that my constant was correct, and that the constant in this relationship is the distance. So I can now rewrite this as the distance over time is equal to speed, and we know that speed equals distance over time. So I've just confirmed this graphically and experimentally. Okay, so now what I want you guys to do is use the data that you collected from last lesson, and I want you to follow the same process that I did and find relationships for, it would have been the mass and the acceleration, and a relationship for the force and the acceleration. So you need to do this process that I've done twice to confirm your relationship of all three variables.